Hi, Math 20s. This is the third and kind of the fourth lesson in proportional reasoning. They're both pretty short, so we group them together. You'll have one more, and then we're basically done what this unit is made up of. So in your notes package, flip to the page that says Scale Diagrams. So scale diagrams are used to represent a smaller or larger object in a new way. The scale that is used depends on the size and shape of the diagram that's needed. So some examples of scale diagrams, probably the most obvious one that you would think about is like a map, right? You can look at the map of the world. It is not the same size as the world. So it's a scale diagram in that you're taking something that's really big and you're fitting it onto something that's more manageable. So a map would be a good example. On the other end, like a scientific drawing from what's seen in a microscope. Is a scale diagram, right? If you're looking at a cell of something and you have it under 1000 magnification, that's actually a scale diagram because you're taking something really small and you're putting it in a way that you can see it without the microscope. So a scale factor, so we'll use the letter K to describe scale factor in this unit. So when you see a K, that's talking about the scale factor, compares the measurement of a shape in a reproduction to the measurement of the actual shape. That probably should also have the word linear here. The linear measurement of a shape in a reproduction to the measure of the actual shape. They're now cleaning the floors at the school, so I'm just going to pause this and go close my door. Sorry about that. Didn't want that weird background noise. So it's a linear measurement. So what you can measure, straight line measurements, basically. So our formula for calculating out a scale factor is your diagram or your reproduction measurement divided by your actual measurement. So sometimes you also see it not just as a fraction like this. You can also see it as a ratio. And so that's a big thing on maps, right? This is a 10:1 drawing or something like that. So that is the way that the ratio will be written is your drawing or whatever your reproduction is. So ratio, you have a colon there, to the actual measurement. Oh, I kind of have written where I want to be writing right now. So hopefully you've scrolled that down, but that's what that ratio can be. Sorry, I'm going to erase part of this. Oh, I could have moved it. Okay, let's do that. So when K is greater than 1, the new shape is larger than the original. And so we'll often call that an enlargement. So like we had above, that would be like our drawing from the microscope, right? We've enlarged it from what it actually is. And then when K is between 0 and 1, so K won't be a negative number, but K can be a fraction between 0 and 1. The new shape is smaller than the original. So we'll often call that a reduction. And so that would be like our map, right? The drawing, the paper map is much smaller than the actual province or city or country or whatever your map is actually of. So let's look at some questions. So in Humboldt, Saskatchewan, there is a 2.4 meter by 2 meter reproduction of a stamp that honors John Diefenbaker, Canada's 13th Prime Minister. Look at us doing social studies and math. What scale factor was used to make the reproduction? Okay, so there was a little stamp that had John Diefenbaker on it, and now they've made some sort of statue or giant version of the stamp. So the stamp is now 2.4 meters by 2 meters, so bigger than most people. I guess some people can be 2 meters tall. 2.4 is a little bit big. Basketball players. So it's asking for the scale factor that was used to make the reproduction. So again, this is an enlargement, right? The stamp itself was small. This is enlarged to be something bigger. And so our scale factor again is K. So that's our scale factor. K is equal to, like we said above, your diagram measurement or your reproduction measurement. Divided by the original or the actual measurement. And so again, just in terms of this question, this is our reproduction over the stamp measurement. So we could calculate it with numbers. So one thing is we need to be comparing in the same unit. So the stamp itself is in millimeters and the reproduction is in meters. So we need to do some conversion. So we know that in 1 meter, there are 1,000 millimeters. So this is actually 2,400 millimeters by 2,000 millimeters. We want to be comparing with the same units. So looking at that, so the shorter side is this 30 and this 2,000. So we'd want to be comparing the shorter side with the shorter side. So we can look at our reproduction. So the big one is 2,000 millimeters divided by the actual measurement was 30 millimeters. Or we could do the longer side as well. We're going to get to the same value. So that was 2,400 millimeters divided by the length of the long side here, divided by 36 millimeters. So dividing both of those out, doesn't matter which one you do, you're going to get to the same thing, that the scale factor is 66.667, whatever, 6 repeating. Or we could do it as a ratio as well. That you could see would be 66.7 to 1. You usually want to have your ratio down in one of the terms being to 1. Yes, you could write it as 2,000 to 30 or 2,400 to 36, but usually you want to have it reduced in the ratio to one of the terms, whether it's the first or the second being equal to 1. I'm still drinking tea when I teach. I didn't even learn that I will spill it all over myself. So the next question, this one will come back, I think actually in today's lesson, or in the second part of today's lesson. So we'll need to remember this scale factor of 66.67 or whatever we want it to be rounded there. So on to the next one, it says Barry applies a scale factor. So this is K is equal to 0.75 to a 12-inch by 18-inch drawing on a photocopier. So what is that scale as a ratio? I'm just trying to get rid of this. So we could write that as, so 0.75. We could write that as 0.75 to 1. We could try to get whole numbers if we wanted to. So making it 3 to 4. But that scale ratio is good here. So remember that a K value equal to between 0 and 1 is going to be a reduction. So that's actually what the next one is saying. So is it an enlargement or a reduction? So scale factor is less than 1. So if the scale factor was equal to exactly 1, that means that it's not enlarged or reduced. It's just a straight up copy. So when I put something in the photocopier, it gives me a scale factor of exactly 1. It should be exactly the same. We can photocopy and we can shrink things down and we can expand things up as well, but like a straight copy would be a K value equal to 1. So what is the final size of the drawing? So using kind of that formula above, if we rearranged it to solve for, let me just flip back a slide or two. So if we rearrange this formula to solve for the reproduction measurement, we know we need to multiply both sides by the actual measurement. So that's your scale value times your actual measurement will give you your reproduction measurement. So we can do that here. So K value multiplied by the actual measurement will give us our reproduction measurement. And so that K value of 0.75, we're going to multiply it by both of those original measures. So one of them was 12 inches, one of them was 18 inches. So if you multiply both of those by that scale factor, we get 9 and 13.5. So the measure of the new, or our reproduction, will be 9 inches by 13.5 inches. So that's our new, the final size of the drawing once it's been copied. And then there's just kind of some scale factor terminology on this next page. So a reproduction that is an enlargement is going to be larger than its original size, and a reproduction that's a reduction is going to be smaller. A linear scale describes the enlargement or reduction of two corresponding similar objects' lengths. So we're just talking in one dimension right now. So linear scale means just one dimension. We'll talk about 2-dimension and 3-dimension as well, but a linear scale is just looking at length. If a scale factor greater than 1, oh, this is like the same thing. If a scale factor greater than 1 has occurred, it's an enlargement. If a scale factor between 0 and 1, then a reduction has occurred. If a scale factor of 1 has been applied, then there will be no change. It's just a straight up copy. So those are just those terms that come up. So that was the first lesson. What did that take me? A couple of minutes. Let's go on to the next part. So getting into 2 dimensions. So in the last lesson, or a few minutes ago, we learned that for a linear measurement, the scale factor K is equal to this. So this was that formula that we had before. So your reproduction measurement divided by your original. We can then use this to determine the areas of 2D reproductions. So this is our formula now. Won't let me click. So now we have K squared. So this is related to K, but now it's the square of it, is equal to the area of the reproduction divided by the area of the original shape. So we'll see how this applies. It's the same sort of idea, but now we're dealing with K squared. So if it asks us for our scale factor, remember that's K. So sometimes we'll need to square root that. So it says Miss Goy has a 5-inch by 7-inch picture, and in a copy machine, she clicks enlarge 110%. So what that actually means is it gives us our scale factor. That's not at all the right letters. Scale factor of 1.1. So that's a little bit kind of confusing, but enlarge 110%. Again, if we said 100%, copy at 100%, that's an exact copy. 110% is enlarging it by 10%. So that gives us our scale factor of K equals 1.1. So if we're looking at those dimensions of the original picture, we need to apply that scale factor of 1.1. So 5 inches multiplied by the scale factor of 1.1, and 7 inches multiplied by my scale factor of 1.1. So our new dimensions of the picture are 5.5 inches by 7.7 inches. So determine the area of the copy. So we know the area of a rectangle is equal to the length of something multiplied by the width of something. So if I take those new values, 5.5 multiplied by 7.7 is equal to, sorry, Alana just walked in with a really cool hat on. Yeah, I'll break my cracker open later. Oh, okay, yeah. So 5.5 by 7.7 is 42.35 square inches. So this is the area of that picture. So your units are in inches squared when we're talking about area. It says, by what percent will the area of the picture increase? So there's kind of two different ways you can look at it. And you see, D says verify your answer to C. So we'll look at first, just looking at our area of our original versus our area of our reproduction. So the area of our new thing, our reproduction, again, we just calculated 42.35 square inches. The area of the original, can't spell, is equal to 35 square inches. So now what we can do is we can find out the difference between these. So 42.35 subtract 35 square inches and divide it by the area of the original. And if we want it as a percentage, we're going to multiply by 100, gets us 21%. So the area, when we apply a scale factor of 1.1 or enlarge as 110%, what we end up with is a 21% increase in area. So what C is saying, verify your answer to C, using that second formula that you have at the top of your paper. So K squared equals the area of the reproduction divided by the area of original. I could be less lazy and write the whole words. So that's that formula that was up top. Come on, extend. There we go. So the area of the reproduction divided by the area of the original, so those two numbers we had in that last question. So when I divide that out, I get a K squared equal to 1.21. So if you divide 42.35 divided by 35, you get an answer of 1.21. So if K squared is equal to 1.21, if I square root both sides, I get K equal to 1.1, which was the scale factor that we had originally up in part A of that. So that verifies our answer that the square of the scale factor will be your increase in terms of area. So back to the old Humboldt, Saskatchewan question. I said we needed to remember that number. And so we had a scale factor of 66.6 repeating. We can use a rounded value So we could do 66.7, but that'll make our answer off by a little bit. So try to keep as many of those 6s as you can in your calculator when you're doing this one, because if you use a rounded value, you actually end up with your answer off by a little bit. So it says determine the area of the reproduction. So again, from that second formula on the last page there, k squared is equal to area of the reproduction divided by the area of the original. So it's asking us for the area of the reproduction here. So if we rearrange this formula, we need to multiply both sides by the area of the original to get our area of the reproduction. So our area of the original is 30 millimeters by 36 millimeters. Our k squared, 66.6 repeating. We want to square that, get our, ooh, good, more loud noises that they're making. I'm not sure if you can hear any of that, but they're like drilling something now. So if I use 66.6 repeating, what I get is 4,800,000 square millimeters. If I do something like, sorry, I'm just going to bust out a calculator, 66.7 squared times 30 times 36. What I get if I instead use 66.7 is I get 4,804,801.2. So you see we end up off by a little bit, because what we could do is we could verify the answer that we have, this answer, with the measurements that we were given for the reproduction. And so that those measurements for the reproduction, remember it was 2.4 meters or 2,000 millimeters by 2,400 or 2.4 meters. And so if we multiply that out, you see we get 4,800,000 square millimeters. So two different ways that you could kind of see that, but again, understanding that formula and how it can be manipulated. Question 3. So Mr. Ostrander is making a kite from a 2 to 25 scale diagram. The area of the scale diagram is 20 centimeters squared. How much fabric will he need for his kite? So this is going to be an example. Sorry. Of an enlargement. Because again, when we write out our, drawing to actual. Sorry, yep. So our enlargement is what we're going to do. So the area of the scale diagram is 20 centimeters squared. How much fabric will he need for his kite? So thinking about how we can get our K value or our scale value. So we know that we can take K and divide 25 divided by 2 is equal to 12.5. So our our scale factor in this case is 12.5. And so again, it's asking us like how much fabric will he need. So we want the area of the fabric that he would actually need. So k squared is equal to the area of the kite divided by the area of the diagram. And so again, if we're looking for the area of the kite, we know we need to multiply our scale factor by the area of the diagram. So 12.5 being our k value squared multiplied by the area of the diagram, which was 20 square centimeters, gets us an area of 3,125 square centimeters. So this is how much fabric he will need to make his kite. So the table below gives us data for enlargements and reductions of a 12 centimeter by 6 centimeter rectangle. Complete the table. So this is, okay, so it's saying we have a rectangle that's 12 centimeters by 6 centimeters. So if we applied a scale factor of 1, exactly 1, remember that just gives you a straight copy. So in order to figure out the area of something like that in centimeters squared, you would take your length, multiply it by your width. So that's how we get to centimeters squared. And if we compared the area of my scaled to the area of the original, well, that would be equal to 1. Because again, k versus k squared, so 1 versus 1 squared is still equal to 1. So the second one here, the only information that we have is that we've applied a scale factor of 3. Remember that if it doesn't tell us, this is our linear scale factor. So we know that we're going to apply a scale factor of 3 to each linear measurement. So a scale factor of 3 to 6 is equal to 18. A scale factor of 3 to 12 is equal to 36. So now to figure out the area of that, so we could go 36 multiplied by 18. That gets us 648 centimeters squared. And so now we could either compare these two numbers, or we could take our scale factor. So this is kind of reflective of our k squared value. Sorry, I've shifted everything. So we could either go 648 divided by 72, or we could go 3 squared. So the area, sorry, just give me a moment. Sorry, I was trying to see if I could get them to stop drilling stuff while I'm trying to record, but we're almost done, so I guess I can be patient. Okay, so the next one. So again, we're comparing it just to this original up at the top. So I see that we now have the length is quite a bit shorter. So we've gone from 12 down to 4. And so that's applying a scale factor of 1/3 or 0.33. So now I need to apply that same scale factor to the width. So again, we're going from here to here. It's getting smaller. It's a reduction, so we know the scale factor is going to be less than 1. So applying a scale factor equal to 1/3 onto that 6 will get me a measurement of 2.0 centimeters. So now my area, if I multiply this 4 by this 2, is equal to 8 centimeters. And my scale factor, again, if I compared 72 to 8, now I have to cough. I can get through this, guys, I promise. So I could either do my scale factor squared, so k squared, or I could compare that 72 to that 8. So sorry, I said 1/3, I meant 1/9. So squaring 1/3 actually gets me 1/9, or going 8 divided by 72 gets me 1/9 as well. So the next one is a little bit tricky because all that we're given actually is our area. So we need to compare that area. So if we went 18 divided by 72, that gets me a relationship between the area of the scaled and the area of the original of 1/4. So we know that we must have a reduction again. So that gives us our k squared. So if k squared is equal to 1/4, if I take the square root of 1/4, that gets me my k value equal to 1/2. So that's my scale factor here. So 1/2 there, and then I can apply it to both the length and the width. So 1/2 of 12 is 6, 1/2 of 6 is 3, and so again, just making sure, yeah, that gets us our area of 18. So that, my darlings, is linear scale factors or scale diagrams, and then into two-dimensional shapes. So looking at area as well. Tomorrow's lesson will be on 3D shapes. It should be a short one, and then you'll have some time to work on some assignments and stuff. So thank you, and we will see you later.